Yeah, first of all, thank you very much for your kind introduction, and especially thank you much for giving us the possibility to give our viewpoint on this fascinating topic of ionic liquids. So, as Ken showed where he is from, maybe this is our Ludwigshafen production site in Ludwigshafen in Germany, and I'm located in this building, in my office. Yeah, it's more or less there, I would say. Yeah, so as I said, I would like to give you a brief overview on our activities with ionic liquids, and hopefully I can answer most of all these questions, which I know very well from many discussions with customers who are thinking about using ionic liquids. First of all, that's something Ken showed already, this strong increase in patent applications and publications on ionic liquids. And I would like to show you some pictures of people who are behind this. So let's forget about the very early times. I would say the modern times of ionic liquids started with John Wilkes in the US, working on electrolytes. Then Ken Saddon, we listened to him already this morning. So I think Ken was starting in the 80s to introduce the idea of ionic liquids in organic synthesis, and with the foundation of Quilt, that was one of the big impacts in bringing the idea of ionic liquids forward. That's Professor Peter Wasserscheid from Germany and Klaus Hilgers. They founded a company called Solvent Innovation. Solvent Innovation's business concept is to make ionic liquids available in kilogram quantities to all researchers in the world. That guy you have seen earlier already, that's a colleague of mine, Matthias Maase. He was the main inventor of the Basel process within BASF. And last but not least, Professor Robin Rogers from the University of Alabama. I will come back to him later. I think there's not really a need to answer the question, what are ionic liquids, after a whole morning listening to some fascinating work on ionic liquids. I personally like most to say ionic liquids, that's nothing else than a new class of chemicals with unique properties. Well knowing the official definition that they are liquid salts with a melting point below 100 degrees Celsius, and all the well-known properties of ionic liquids. At this point, I would like to come to a very important point, and that are the extraordinary dissolution properties, and especially their ability to dissolve cellulose. And I also would like to show you a film here. Oh, it's not working. Why? Okay. So no film? You can make it big. I think this a small arrow.
Down to the right.
This one here. Yeah, perfect. So what we have done here in the lab experiment is to dissolve cellulose, a filter paper, in an ionic liquid. It's totally dissolved, and afterwards, by adding water, you can re-precipitate the cellulose. And as you know, to dissolve cellulose, that's not so easy. And there are not so many solvents who can do that job. And we think with ionic liquids able to dissolve cellulose, we have something in our hands, again, enabling us to go further to green processes in processing cellulose. Yeah, so maybe we go back to the PowerPoint presentation. Yeah, thank you. So not all ionic liquids dissolve cellulose. You need specific ILs. It mainly depends on the anion, whether an ionic liquid is able to dissolve cellulose or not. You easily can bring in 10 to 15% of cellulose in the solution in the IL. In some experience, maybe even more. When I first heard that, I thought, okay, that's a kind of degradation of the cellulose and then it's dissolved. But it's not. Believe it or not, it's really a dissolution of cellulose without degradation. You can also have degradation if you want, for example, if you use an acidic ionic liquid, but normally no degradation. And also very important, if you are thinking about commercial processes, that's really a stable solution. And as I have shown you in the short video, can be reprecipitated just with water or alcohols. Described in a patent of Robin Rogers from the University of Alabama. And last year we acquired an exclusive license on this patent because we believe that this is a very valuable tool in making processes for cellulose more efficient. So, and now it works. Interesting. So, we heard already a lot of properties of ionic liquids this morning. And so it always starts with a melting point. And what I would like to show in this chart is that you always have a broad range in the properties of the ionic liquids. So for example, the melting point can be below -20, but it can be also above 100, well knowing that's not an ionic liquid even then by definition. And the same is true for all the other properties of ionic liquids, as we have just heard by Professor Uwe. Viscosity, you can have liquids with a very low viscosity or with a very high, and it will always depend on your application, what you need. And so that's the same for all these properties. And can maybe you correct me, but as far as I know, there's no ionic liquid existing which gives you the optimum in all these properties.
I think that's absolutely correct.
Yeah, so we are working on that, but I think that's not possible. Yeah, so you will always have a kind of a profile, and So this is a real example. Yeah, so we got an inquiry from a customer, and he was focusing on these 7 properties, and he has a very clear understanding what the property profile has to be. So that's what we sometimes get from customers, and what we are doing then is we first select some candidates which we think can do the job. Then we supply kilogram samples. The customer carries out some use tests, and in this case the ethyl-methyl imidazolium ethyl sulfate was chosen as an optimum, and that's now produced in a ton scale on our side for this application. Unfortunately, I cannot tell you in detail what it is because we are under secrecy agreement here. But just to show you how this works. So, as I mentioned already, every ionic liquid will show a specific property profile regarding all these properties. And also important to know is that there are already 3 ionic liquids which have been registered regarding the European chemical legislation. That's the so-called E-links registration. That has been done by initiatives of Degussa and BASF. And so these 3 ionic liquids are fully registered, and though we can sell them already in ton quantities. And we are prepared to do the same with other ionic liquids if we see interesting demands coming up. So how to get an IL produced in ton scale? Normally that starts with an inquiry from a customer. Then, as I have shown you in that example just now, we start with a product selection, discuss the basic specification, then we decide whether we can do that or not, and all that normally is done under a secrecy agreement. In the next phase we go into our labs, produce first kilogram samples, also some basic tox data and price calculation. Then it goes to a pilot plant stage. Here we produce 100 kilogram sample. We finally define the specification. We decide in which plant we are going to produce the product, notification, and negotiation of prices and the supply contract. And finally it comes to production on a ton scale, and we supply product then in spec and on time. That's, I would say, the most frequently asked question. What prices for ILs can be expected midterm? So please keep in mind, today we are here. Prices for ionic liquids are in the range of 100 euros per kilo. But that's not specific for ILs, that's specific for all chemicals produced only on a very small scale. And I think that's a very important point, because you can often read ionic liquids are too expensive for commercial processes. That's stupid, because it's simply not true. If we are able to increase the production quantity per batch, the prices definitely will go down. And we today think will easily go down to prices of, let's say, 20 or 30 euros per kilogram. It will not be the same as for very cheap solvents in the range below €1 or $1 per kilo, but will be affordable. And that's one of our goals within BASF, to have processes in our hand allowing us to realize this cost reduction. And on the imidazolium salts, that's clearly one focus in our work today. We have that already. So Ken showed you a nice picture of our imidazole plant. That's a plant which is a flexible multi-product plant with a capacity of some 1,000 tons per year. And in that plant we can produce alkyl imidazoles. Alkyl imidazoles as the basic raw materials for the production of imidazolium salts. The next step then is an alkylation reaction, maybe with chlorides, maybe with alkyl sulfates or phosphates or whatever. If you are lucky, you may get already your desired ionic liquid. If not, there may be the need to exchange the anion in an anion exchange reaction. Primarily goal will be to get this in one step, but sometimes it's necessary to have the second step. In principle, this is also applicable to other nitrogen-containing compounds, or also to phosphorus or the sulfur compounds. But as I said, our focus at the time being is on the imidazolium systems. And that's something where we also have already experience in production in ton scale for external customers as well as for internal customers. We are also working on some other cation systems, like the simple ammoniums or collinium, pyrrolidinium or pyrazolium. We have spent not so much time and energy on sulfonium, phosphonium, on pyridinium, but if we come across with them, that's not out of the picture, but it's not in our focus at the time. So, next chart shows you what you can do with ionic liquids. Over this morning, we heard already some examples for applications of ionic liquids. And this is a little bit our picture within BASF. So we are concentrating on three segments. The first is chemical processing, and that was the starting point for us to think about ionic liquids. The second part I like to call performance chemicals. Here you use a specific property of the ionic liquid in an application. Here you also find the electrolytes, or you can use them in processing metals like aluminium, or you can simply use them as functional fluids like lubricants or whatever. And last but not least, what I have shown you with this short video, the property to dissolve cellulose opens a broad range of possible applications here. What's today already realized, Degussa has published to use ionic liquids as a kind of compatibilizer or a paint additive. That's commercialized. Ionic can show you that also use ionic liquids as an antistatic additive in a cleaning fluid, air product, storage of gases. And Linde just recently announced that they use an ionic liquid as an hydraulic liquid in the compression of gases. I'm pretty sure there are already more applications realized, but they are not yet published. In chemical processing, I always like to show this chart because that's, I think, very, very true. I'm not sure whether you have said that to them. Really, you did? Okay. So sometimes with interviews it's a little bit difficult, but in this case I think it's really true.
I always make sure that I see it before they
Okay. Yeah, and so I think that's very, very true. And ionic liquids are a very valuable alternative tool in the toolbox of organic chemists. And again, what's realized here? IFP, olefin dimerization, Degussa, hydrosilylation, Chevron Phillips, olefin oligomerization, and within BASF we have 3 processes which are at least realized in pilot plant scale. And again here, I'm pretty sure there is already more. So that's something you have seen already in a nice video. That's our BASF process with this sticky slurry in the original reaction with the amine. And what we did here is we just changed the amine going to the methylimidazole, allowing us to have a liquid-liquid phase separation by building the imidazolium chloride.
That's when your ionic liquids is black.
Yeah. So normally it should look very clear. So those of you who remember the presentation of Ken will remember this very nicely phase separation. Also important to mention here is the ionic liquid here, the imidazolium chloride, can be recycled very easily. In this case, just by adding sodium hydroxide, you can get back the methyl imidazole. So this process is working continuously with recycling of the ionic liquid. And yeah, so in former times we used such a conventional reaction vessel for this reaction, and by the increase in the yield per volume and time unit, we are today able, that's not really a microreactor, but a very small jet reactor. So that's a chlorination of alcohols. So normally we use phosgene for this reaction. If you try to do the same reaction just with HCl, you end up with a terrible mixture. Surprisingly, if you do the same in an ionic liquid, you get a very high yields and a very high selectivity, the desired dichloride. And that process works very nicely. So it's done in a typical vessel, and you start with a homogeneous mixture of HCl, the alcohol, and the ionic liquid. And after the reaction is finished, you end up with the chloride as the upper phase, and the ionic liquid and the water, which is built during the reaction, as a lower phase. And so, just by distilling water, you can reuse the ionic liquid. And we have done that many, many times without any loss in selectivity. And this process will be realized commercially mid of this year within BASF for the production of an intermediate and chloride which we need internally. Last example, extractive distillation. For breaking azeotropes, like for THF water, you have to use an extractive distillation, and in the extractive distillation you use an entrainer, which in this case takes care of the water. So the water will end up in the bottom of your distillation column, but you have to have a second distillation column here in order to get your entrainer back. If you now use an ionic liquid, there is no need for the second distillation column, because as the ionic liquid has no vapor pressure, you can just simply flash the water or the lower boiling compound and recycle the IL. And as Ken already said, our ILs are normally black. So this is the IL we used in this process for 3 months in the pilot plant. And temperature here is up to 250 degrees, so relatively high temperatures. And so it's not surprising that the ionic liquid turns black, but it doesn't matter. So there was no need for any purge of the ionic liquid. You can just recycle and the process is working, and the desired product is absolutely colorless. So that process is applicable for a broad range of azeotrophs. So we have tested that for some examples, and the principle is always the same. You have a less polar component A, which you get at the top of your extractive distillation column, and you have a polar component, an ester, an alcohol, or simply water, which by the help of the ionic liquid will end up in the bottom of the distillation column. So, last but not least, again, a very often asked question, how to recycle ionic liquids. One example I have shown you already. In the case of protonated ionic liquid systems, you can use our BASF recycling by adding sodium hydroxide, getting the imidazole back, and then by reaction with HCl or in general HX, you get back the ionic liquid. Okay, that's a very special one. That's, I think, in many, many cases, what you will do. You will just recycle the ionic liquid as it is, and you will take off a small purge and send it to the incineration. So I was very happy to see your video that ionic liquids can be burned, because we are very often asked how to dispose ionic liquids, because I cannot burn them. That's not true. Yeah? If the temperature is high enough, you can incinerate the ionic liquid. So this, I think, will be the most often used process. For example, the extractive distillation. Yeah? So we can recycle the ionic liquid for 3 months. Okay, at the end, that will not work for years. If you carry out such a process for a longer time, there will be the need to purge a small part of the ionic liquid. And so I think that's a very nice way. Another possibility, ionic liquids can be distilled. That's also true for this one here, for our BASF ionic liquid. That can be also distilled. And as we have heard already this morning, there are some other ionic liquids which you can distill. I think that can be a very valuable tool in chemical processing. If you can distill your ionic liquids, and all the byproducts can be get out of the process on this way. Last but not least, if the ionic liquid is not distillable and at high temperatures you will get a decomposition, but that might be also a valuable tool for recycling of the ionic liquid. So it will depend on the ionic liquid, it will depend on the process, but overall we believe there is not a so big hurdle as some people believe to get to recycling of ionic liquids, which you definitely need in order to make such a process economically really valuable. So that was a brief overview on our activities with ionic liquids, and hopefully I could answer some of the questions you may have had. And if there are more questions, please let me know today or also later. And for the time being, thank you for your attention.